Hello, I'm Simon Mackin.
My name is Deneau.
And I'm Spencer Cobb. We are all students of the Engineering Academy in Traverse City, Michigan, and we are competing in the manufacturing Workcell competition. We are Team Wok-Cell.
Our Workcell is designed, built, and programmed to cook stir-fry based on a user's input. We chose this idea because it would meet the growing commercial needs of automatic cooking systems in restaurants throughout the country. From the very beginning, the three of us had decided on a Workcell project that would cook stir-fry. Since then, we have followed the Plan, Do, Study Act, or PDSA process, to help guide our steps in making this project come to life.
For the plan phase, we looked into the current situation, including criteria and constraints for the Workcell project. In addition, we identified the problem or prompt of the contest, creating a strategy plan for brainstorming and designing a few of our systems in CAD, and split up proficiencies for each person on our team, me being on CAD, Simon on programming, and Spencer on electrical. For the do phase, we put our plan in action by getting materials together from around the tech lab and ordering necessary parts online. Once we had sufficient parts, we moved on to constructing, programming, and wiring up our systems.
When our systems were operational, we started to diagnose any issues we may have had with wiring or if design parts were not fitting or working properly. During the study phase, we also collaborated with Skills Manufacturing Aerospace, SMI, on our networking issues. Once these issues were identified, we made several revisions and finalized parts of our systems until they worked properly. This was the ACT phase of our Workcell. The human-machine interface, or HMI, is used to electronically control the user's input for what their dish of stir-fry would include. The touchscreen utilizes buttons for individual ingredients for an easy input experience. The programming for the HMI is done in the Seymour software.
From there, this stock FANUC robotic arm will be performing the majority of the mechanical functions in the Workcell, including managing the ingredients, cooking the food, and pushing the food off of the cooktop to be served to the user. The FANUC toolhead is multi-purpose, utilizing a pair of 3D printed jaws, which grip the boxes containing servings of food, and also uses a spatula to stir and maneuver the food around the cooktop. As is being shown in our demonstration, the FANUC arm will work in conjunction with the fridge door opening and closing to grab one of the boxes, and then maneuver it to the cooking surface, drop its contents, and then return the empty box to the used container below the fridge. What's showing now is the stirring program. The FANUC uses its spatula to push around any contents of the pan. The purpose of this is so that the food cooking does not remain stationary for the entirety of its cooking time, and is instead rolled around to make a much better cooked meal as an end product. Our final demonstration is our pushing program. This is how the food will be output when it is finished cooking. The FANUC utilizes its spatula to push off the contents of the pan into the chute of our cooking assembly, where it then drops into a bowl to be grabbed by the user upon completion.
Working in the background, we have the PLC, acting as the main electrical brains between the different systems. The PLC operates and coordinates all priorly mentioned systems within the Workcell. The programming of the PLC is done through the Productivity Suite program using ladder logic. The PLC communicates to the FANUC and HMI via Ethernet on a network. Along with just the PLC, the electrical box also houses other electronic components, including the input and output cards for the PLC, a 24-volt power supply, fuses to ensure the electronics are safe, a 120-volt relay to control the heating unit, buck converters to lower the voltage to the fluid pumps, and multiple distribution blocks for positive and negative leads. All of these components in the PLC box are mounted on DIN rails, allowing for easy organization of components.
The fridge works in coordination with the FANUC arm and helps to keep the stir-fry ingredients cool until they are cooked. We decided to use a standard wine fridge as it maximizes both the height and depth, yet minimizes the width, allowing for less points to be programmed per ingredient on the FANUC. On either side of the fridge, we have single-action pneumatic pistons, one to mechanically open the door and another to close it, each controlled inversely by an electronic relay valve.
Due to some networking issues between the FANUC system and PLC, we have not been able to coordinate programs between the two systems. SMI has been helping us on our process through programming and setting the FANUC up. At this time, however, all of our systems and programs only work separately, which shows that if proper communication was present, they could indeed work together. These containers house the oil and sauce for the stir fry and are dispensed via the mechanical fluid systems located at the bottle caps of each container. The oil will be dispensed directly before the food is to be cooked, and the sauce will be put on near the end.
This assembly shown is where the cooking and output of the food will take place. A heating unit is located in the chassis in contact with this cooktop shown, on which the food will be heated. When the food is done cooking, the FANUC will push the food into the chute shown, falling into a bowl or plate for the user to enjoy.
For our student-built parts, we have our fluid container system, our bowl stand assembly, our cooking assembly, as well as attached output, our FANUC tool head gripper, as well as our spatula mount, our fridge pneumatic systems, which are located on both sides of our fridge, and our wide array of 3D printed parts. All of these parts went through many iterations during our development process, which includes our grippers, as seen on the left, and our shelves on the right, as well as all other 3D printed items.
As you can see, a Workcell, 27.5 inches by about 47 inches, which is firmly within the 15 by 15 footprint.
In addition to this presentation, we have also sent over additional documentation to help aid you in your judging decisions.
If you have any questions, we're open to an online meeting or can provide additional documentation if necessary.
This has been Team Wok-Cell, and we thank you all for listening. All three of us will be attending the competition this April, and we would be glad to talk about our project then as well.